Sorry, we had a low battery issue. We had to kind of
My bad, y'all. My bad.
revamp the camera. All right, so this is your classic solubility curve. Okay. Now, when we're looking at a solubility curve, okay, notice the solubility of most are increasing, but they all don't increase by the same amount. The bigger the value of delta H, the more positive it is, the steeper the curve. So when I look at NaCl, which is nearly horizontal, very little difference in solubility with temperature, that means this delta H is pretty close to 0. Now it's positive, it's going up some, so it's not going to be 0, it's going to be, but it's going to be a very low number. What do we know about the sign of cerium sulfate? Positive or negative? Negative. Which other ones? There's not another negative one on that one. Okay? So, notice on the y-axis, it's going to be solubility in grams of salt in 100 grams of water. You've got to have an amount of solvent that you're putting it into. You can't just say this many grams will dissolve. Well, how much water? Is it a cup of water? Is it a gallon of water? How much water are you putting in it? What's the ratio? So if I'm looking at this, just to read this graph, KNO3 at 40 degrees. What's the maximum that can go into a solution at 40 degrees?
So which one?
Oh, wait.
KNO3 at 40 degrees. That's right. I would say it's not quite for sig purposes. 65 would work because you're allowed, but I would say it's just a hair below halfway. So 63, 64, somewhere in there. Remember, the last digit's always uncertain. Now that's the maximum you can put in. When we talk about solubilities, what does it take to make a saturated solution? What's the maximum amount? Okay, so 63. What would it be for sodium nitrate at 20 degrees? NaNO3 at 20. About like 88. Okay, so we can read that graph, right? Everybody can read this. Okay, so that's pretty straightforward. This just gives us solubility of different things. Now, what if I said, okay, so it's 88, which one did I just say? NaNO3 was about 88 right there. What would it be in 200 grams? How much would dissolve in 200 grams? That's per 100 grams. Just double it, 176. How much would dissolve in 50 grams? 44. So it's a ratio that's going to be, solutions are homogeneous, so it doesn't matter. It just gives us the ratio of how much combines. So this one table, we can then figure out how many grams would be soluble in any amount of water. We just set up the proportion. 88 is to 100 as X is to whatever you want. Okay? All right, so that's all just kind of the qualitative stuff. But I know you guys want to be able to do some math and be able to do some stoichiometry with this.
Yeah, I was waiting for that.
I knew it was coming. I knew it was coming. I was like, what are we going to do worksheets on if it's not math?
What's the math part?
Oh, God.
And then
Does SEC basis, does that unit have math in it?
There has to be a more quantitative way of measuring concentration. And we have two main ways, one main way and one minor way. Well, there's a bunch of minor ways, but we're only going to learn about one of them. Maybe two. Since Mr. Graber did it, I feel obligated that we need to. But it'll be a quickie. But the main one is molarity, which is represented by a capital M. And you may have seen that on some of the bottles in a lab. Talked about 2 molar, 6 molar, 6M. And that is a ratio of moles of solute, this is not in the notes, sorry, over liters of solution.
I mean, there is something that says molarity.
That's molality on free, isn't it? Oh, that's on osmotic pressure. Yeah, but.
There's something different.
Well, it's the same molarity, but it's not how to calculate it. That's just using that in that thing. That's going to be at the very end.
Okay.
Okay, so molarity is moles of solute. Now we can't go and measure moles, so how do we change grams to moles?
Over mass.
So it surely can say grams over molar mass over liters is equal to our molarity. That's really our best working equation. Now, why is this important? If I have moles per liter, what's that going to conversion factor between? No. And if it's moles per liter, what's that a conversion factor between?
Moles and liters.
Moles and liters. Okay? Molar mass is grams per mole, so it's a conversion factor between grams and moles. Density is grams per milliliter, mass over volume, so it's a conversion factor between grams and milliliters, mass and volume. Whenever you have something with two units on it, it's a conversion factor between those two things. So moles per liter can be a conversion factor for us if I'm given a solution volume instead of grams. So instead of using the molar mass to convert to moles, I can use the given molarity. And so it actually makes it a lot easier in the stoichiometry, because we don't have to figure out the molar mass. The molarity is almost always given. Okay? So, example. What is the molarity of a solution which is made by adding into enough water to make 500 milliliters of solution. Okay? Question mark. All right. Now notice on the wording, I'm not adding 500 milliliters of water. I'm adding enough water to make 500 milliliters because this 171 grams is going to take up a little bit of space. Molarity is liters of solution, not liters of solvent. Okay? So you add water. Now generally what you would do is you would use a thing called a volumetric flask. This says 100 on it right here. This is a 100 milliliter volumetric flask. It's got one line on it. If you fill the water up to that one line, how much do you think's in here?
200.
Well, if it's a 100 milliliter flask.
I thought you said 100 at that line.
No, right here at this line, right here.
Yeah, 100.
Okay, this is 100, so it's a measured volume, one volume, a volumetric flask. So you would add your solid into here, and then add the water, and generally you add it about 2/3 full so you can swirl it and get it to dissolve. Then you just use like a wash bottle or something, you fill it up to where the bottom of the disc is on the top of the line. Then I know exactly that I have 100 milliliters of solution, and I know exactly how many grams I put in, so I know how many moles I put in. So I would know the concentration of this. Now that concentration is going to be consistent. So if I pour 5 milliliters out, that 5 milliliters is going to be just as concentrated as this. Okay, so now I know the concentration of my solution. So what do we do here? Molarity is going to equal what?
171 divided by 340.
Divided by what? What do we divide it by? How much, Madison? 0.5. Now, you should be able to do mental math. 171 divided by 342 equals 0.5. And that's really 3 sig figs. So we're going to get 1 mole. So I would know that in my 500 milliliters, okay, well, if I had a liter of it, I'd have 1 mole. 500 milliliters, I'm gonna have a half a mole. 100 milliliters, I'm gonna have a tenth of a mole present. It gives me a quantitative way to know however much volume I have, I can know how many moles are there if I know the molarity. Molarity times volume always equals moles. Molarity times volume equals the moles of solute. Now, Friday and Monday, you're gonna get to do some molarity problems. I'm not gonna go through and do a whole bunch, but it's just plugging into the formula. You got 4 variables, 1, 2, 3, 4. You're gonna be given 3, you gotta find the 4th. Okay? So you just gotta go through, sometimes you'll be given moles, sometimes you're given grams. And so you just plug in. And you practice that on Friday, Monday, and then on Tuesday we'll go over all that and make sure that we fill in any blanks. Okay? You know, I'm counting on Caroline that she'll be able to. She'll be making the rounds on Friday and Monday. That's why I'm gonna leave for the substitute. I'm gonna leave notes. Yeah. If anybody has any questions, just tell them to ask Caroline.
So the test is Thursday.
Ideally, we'll see. I'll let you know specifically on Tuesday, but
Is this the only math that's on?
no. So.
Just don't ask
Let's
me a
put
question
some stoichiometry
until I'm done
into
with the
this.
worksheet.
Nothing like a solid, yes.
Oh, I thought that was.
No, that's just calculating molarity.
I was like, that's
Molarity is the conversion factor. And if you need to put this out here, it's a conversion factor between what?
Moles and liters.
Moles and liters. So, what mass
I'm so tired
of
of seeing that.
what mass of AgCl
Yeah, it started with that.
will be
Every time I see it, it just makes me sad.
It's okay, man.
when 50 milliliters of a 0.250 molar AgNO3 solution is reacted with excess calcium chloride. I'll just put CaCl2. All right, now, if you want, you might want to get out your stoichiometry roadmap because this is on there if you want to look at that, but you may not need to, okay? But the first step in any stoichiometry problem is write a balanced equation. So we know that silver nitrate, that's a solution, is reacting with an excess calcium chloride solution. And what's that going to make? Tell you one of the products.
2 AgCl
It's going to make 2 AgCl solids.
and calcium nitrate with 2 parentheses 2.
Okay, and I know that that's aqueous because it's a nitrate and all nitrates are soluble. I need a 2 out here. Okay, so that's step 1. Step 2, what am I given? What am I looking for? Okay, I'm given 50 milliliters. Let me do it in a different color. 50 milliliters of a 0.250 molar. What am I looking for?
AgCl.
Grams of AgCl, grams. And I like to put the unit so I know that when I get to that unit, I'm done. Okay? Now, the only thing that's different on this stoichiometry problem is what we're given. If we are given grams, we convert to moles using the molar mass. If we had a gas at STP, well, how would we convert to moles?
22.4.
22.4. If I have a gas not at STP, how do I convert to moles?
Pivnart.
N equals PV over RT. But now I have a solution volume. This is the last part of the stoichiometry roadmap that we hadn't covered yet. A solution volume. So molarity is my conversion factor between volume, liters, and moles. So I start with my liters, but we should be able to convert this. How many liters is that going to be? 0.0, it was a letter. 0.0500 liters. So now this is my conversion factor. Capital M stands for moles per liter. So where does liters need to go? So I'm going to say 0.250 moles for every 1 liter. Now everything else is exactly the same. What's the next step? Mole ratio, right?
Does it say 0.0500 liters?
Yes.
Is that a K? I can't read.
No, that's a liters with a cross through.
Oh, gotcha.
It canceled.
Okay.
Gotta stay with me. Okay, so mole ratio. It's always what we're looking for. AgCl over what's given. Okay, then how do I go to grams?
Molar mass.
Molar mass, 143.35. So now I have grams of AgCl, which is what I'm looking for, so I stick a fork in it because I'm done. What does that come out to? How much? 7.39. 9 grams AgCl. Okay, so you'd expect to collect 1.79 grams on your Phillips paper. Again, don't overthink this. We just have another conversion factor to moles. That's all molarity is. So if you're given solution volume, you use molarity to go to moles. Now we can go the other direction too. We can say, what volume of lead nitrate, what volume of 0.1 molar PbNO3 solution is needed to react with 15 grams Ki. Now again, if you look on your stoichiometry roadmap, you're given grams this time, and you're looking for solution volume. So we're basically going in reverse. Okay? So, what obviously was the first thing we need? What's reacting with what? And that will make?
KNO3 with a 2 in front of it, and then PBI to PBI2.
Which one will be my solid?
Yeah.
Yeah, because this is an alkali metal, this is a nitrate, so I know this is aqueous. So this is my solid. Okay? So I'm given 15 grams of this. I'm asking for X volume, I'm going to say liters, of 0.1 molar. Oh, there's a 2 right here. Now, since the X is on this, that's my unknown. That's my given. Right? So, what do I start with?
You have to find the mass
Well, I start with 15 grams of Ki, and then I use the molar mass of Ki. Somebody just, it's 39.1 plus 127.9?
126.
126.9, I'm slacking up again.
It's coming through now.
127 plus
166. Okay, so we're gonna put 1 mole over 166 grams here. So that gives me moles of Ki. What's my next step? Mole ratio. 1 mole PbNO3 for every 2 moles Ki. Now this time I need to go to solution volume, not to grams. So what's my conversion factor? 0.1. But notice that moles have canceled, Ki has canceled, so I'm left with moles of it, PbNO3 on top. So where does moles need to go? So I'm gonna say 1 liter over 0.1 moles. Moles cancel, leaving me with liters of lead nitrate, which is what the question is asking for. We're almost there, y'all. Almost there. What do we get? 162? 462? 452 liters, really?
0.452.
Oh, 0.452. Which is gonna be liters, which would be how many milliliters? 452 milliliters. Now, the question did not ask specifically for what unit. So you could have left it in liters, that'd have been fine. But if the question asks, we need to be able to convert between liters and milliliters pretty easily. Just move that decimal 3 places. Do you have a question? You just tried. Okay. All right, so stoichiometry with molarity, nothing really new. Just gives you a conversion factor, and most of the time the conversion factor is given. Okay? Yes, sir.
At the end, why, it's like 1 liter over point.
0.1, because it's given, the concentration is 0.1 capital M, that's 0.1 molar, mole per liter. And it's always that many moles over 1 liter. Okay, so you'll have a worksheet to be able to practice some of those. Okay? So you got a worksheet to practice just molarity, you're gonna have a worksheet to practice molarity and stoichiometry. Okay? Let's look at the last thing, the fun thing.
That word's never what it means when it's started in this class.
I like that. My definition of fun isn't always your definition of fun.
Oh, anytime you hear now it's time for the fun part, that's when you go, oh crap.
Yes.
This is gonna be brutal.
It's actually not. This actually is gonna be. You guys are gonna appreciate this.
Mr. Hobbs, like the last day of school, can we do the Chick-fil-A ball thing again? Can I?
Well, the problem is that liquid nitrogen is expensive.
Can I throw it? Like, I feel like when you threw it, it just like, would it break a car window?
Oh yeah. It could. No, I don't know. It shatters pretty easily. So.
Well, I mean,
So
like, if I took
it's gonna absorb all the energy, not.
It's like, would it get warm enough to, before it hit the ground? Like, if it was 95 outside and I threw it out the window, would it get warm enough to before it shattered?
What's the sign? I know this is kind of tough. What's the scientific reason why if you throw the spark plug at a window, the portion part it breaks, shatters the window, but not the metal part?
What?
Like where you throw the portion part of the spark plug and it shatters the window, but the metal part won't. Like,
Really?
why is it?
I've never heard that, so I don't know. Maybe the porcelain, I mean, the pointy part is the porcelain part. So maybe it's just more force going into a smaller area on that versus, you know, the round threaded part is not quite as much energy. I mean, the energy is more dissipated across greater surface. That's a quick guess. I'm not sure. That's.
It doesn't make sense.
All right, a second way of calculating
The science behind car robberies.
is molality, little m.
Why do people come up with words like this?
Molarity,
Yeah, this
molality.
dude.
What
really
is
couldn't
the
think of
reason?
A new word.
Sounds like you're saying molarity with this.
Molality.
He's like, this isn't already confusing enough. Let me change one singular letter.
Okay, so the only thing that's gonna be different is still moles of solute, but this time it's gonna be kilograms of solvent. So 100 grams of water would be how many kilograms? 0.1. Okay, so we need to be able to do that grams to kilograms. So we're gonna do this exactly the same way. The only thing that's different is grams over molar mass. It's over kilograms this time instead of liters. And this is kilograms of solvent, not solution. So this is actually how much water you add. Now, the only time we ever use this is when we have doing problems with what's called colligative properties. Now, this is in the notes. Colligative properties, and at the same time, because we only have like 5 to 7 minutes left of me talking.
Break the last sentence everyone.
No,
No, we're the
I have
lab.
to be done. I have to be done.
I know, that's why I'm also like extremely confused.
No, we get lunch
Okay.
at 1:30. 5.
Oh my god.
No, but this, you're gonna run out of time.
And I'll have to watch another lab video.
No, it's- this one you're probably gonna win.
Thursday lab.
Well, there's actually 2 videos.
All right, properties of a